So hello and welcome to my presentation, Automated Bootstrapping of a Fault-Resilient In-Band Control Plane. My name is ermin.sakic and I'm affiliated with Siemens Corporate Technology in Germany, as well as with Technical University of Munich. So the main idea behind this work is to introduce novel bootstrapping schemes for in-band control of resilient SDN networks, basically where we assume a multi-controller design with requirements for automated interconnection of the controllers, as well for automated interconnection of controllers to switches using resilient open-flow channels. In our bootstrapping approach, we specifically aim to support industrial networks. Industrial networks, due to their quality of service requirements, as well as the high dependability requirements on high availability of the control plane and data plane elements. Additionally, the industrial networks require high topology dynamic support for instance, in factory automation cases where factory cells might need to be attached or detached during runtime, with these cells actually being small-scale layer 2 or layer 3 networks that interconnect to a backbone, which is also an SDN backbone potentially in the future. The TSN group, working group of the 802.1, has recently standardized a set of amendments to the 802.1 standard, Q standard, specifically targeting the requirements depicted above. And these mechanisms introduced there vary from time-aware shaping to stream policing, as well as frame preemption and replication and so on. They additionally standardize a set of control plane mechanisms used to actually configure these properties of the system. So the centralized network control is very reminiscent of the SDN architecture, where a single function is responsible for collecting the data of the system, collecting the statistics, and based on observed data and based on its inherent knowledge of the capacities or capabilities of the individual TSN forwarding devices deployed in the system, configure these devices appropriately to fulfill the requirements at runtime. The runtime requirement also introduces the need for a highly available centralized network configuration, and in industrial settings it is always necessary to deploy these controllers in in-band manner due to associated costs related with cabling for harsh environments. Out-of-band networks are not preferable. So the following topologies are some typical industrial topologies which might also rise in future TSN deployments, varying from star to ring to grid topologies. Some are more specific to utility networks like the grids, while the ring networks and daisy chains might be more and more often found in factory automation. This is one example of a production network where SDN was recently deployed due to the network visibility it offers, as well as possibilities to establish a multi-tenancy based approach to stream management. And it basically relies on a common backbone, ring-based backbone, with a number of line topologies which are specific to the individual turbines in this wind farm control network. The control system based on off-the-shelf SCADA, which communicates with individual controllers in the turbines, was the hosted application in this scenario. For more details about this deployment and the open-flow switches used in this deployment, please refer to the project website for each event. There exist two approaches to designing a SDN control plane. On one hand, it can be an out-of-band control plane where the data exchange between the controllers and the switches is hosted on a dedicated management network. This approach, of course, comes with additional capital expenditures due to the requirement to have an isolated network. With in-band control networks, the substrate used to exchange the packets between the controllers and the switches and between the controllers is the same as the one used to exchange the packets between the end applications, or maybe IoT devices in the industrial scenario. Due to the lower costs and complexity reasons, in-band industrial networks are preferable for industrial deployments. The goal of the overall bootstrapping approach is then to automate the establishment of such a setup with regards to the functional and resilient requirements of the control plane. Specifically, we require initial control to switch and control to controller connection establishment in automated manner. The control plane fault tolerance must be provided as an end result of the bootstrapping procedure. The full topology must be available for management and control for all the controllers, but also the individual links and ports should not ideally be blocked due to the particular requirements on highly available stream or flow establishment, which might require more than a single tree. And network extension should be supported, as well as the overall approach should be ideally compatible with current implementations of OpenFlow switches. Some assumptions we make on the resulting system is that switches must be plug-and-play manageable, which means attaching switches to an already existing running network should result in its eventual deployment in the control plane, which basically requires an approach to handling switches that are not aware of the controller lists. Additionally, the controllers might know about the IP addresses of the other remote controllers, so to whitelist them when establishing a cluster membership, for instance. And the switches and controllers can optionally exchange the public key infrastructure certificates in order to provide for authentication mechanisms. So the proposed approach to control plane bootstrapping in terms of very high-level steps is relatively straightforward. So the controllers are supposed to distribute the IP addresses to switches from a common pool of addresses. The controllers provide each switch with controller lists, so for instance, OpenFlow controller lists, and the controllers establish eventually the control channels to each switch. Specifically, in OpenFlow, the switches establish the OpenFlow sessions to the controllers, or they trigger the session establishment, but eventually all the controllers and the system should be capable of connecting to every switch in the system for the purposes of high availability of the control plane instances. Some of the resilience requirements we assume here is that the control plane must be able to tolerate failure of F of 2F+1 controller failures, and we assume fail-stop controller failures only, so no Byzantine support currently. And the data plane must also be able to tolerate k-element failures, specifically when k+1 fully disjoint paths are available in the system, we can tolerate up to k-element failures. Otherwise, the maximally disjoint paths should be provided for the control-to-controller communication as well as for control-to-switch communication. Now, bootstrapping of a control plane and data plane in SDN introduces an inherited codependency when bootstrapping in-band control networks. Specifically, to bootstrap a SDN network, we eventually have to bootstrap it with the flow rules, table rules, which should enable the interconnectivity and network extensions for switches added in the future. But in order to configure the flow configurations or to configure the flow tables of the OpenFlow switches, the controllers might have to synchronize. For instance, in OpenDaylight and ONOS, a strong consistency requires synchronization of the registry state of individual controllers, including the flow table state, in order to ensure that all the controllers have a consistent view on the flow tables of the switches. Hence, we have to be able to bootstrap the controllers prior to configuring the flow rules, which requires controller-to-controller communication, which, of course, in an in-band setup requires connectivity over a data plane. And then we come into this loop where the control plane and data plane are codependent with their configurations. In order to break the loop, we basically introduce a multi-phase concept to overall bootstrapping procedure by, prior to establishing the control-to-controller communication in the system, we partially bootstrap the data plane autonomously. So we present in this work two automated bootstrapping schemes for a reliable multi-controller in-band control plane establishment. One is based on the assumption that we have distributed protocols for spanning tree computation provided in the data plane. So this is the hybrid switch approach. The other one is a hop-by-hop approach, which assumes the RSTP are possibly unavailable, which limits the complexity of the overall system implementation. There already exist a number of approaches for bootstrapping in-band control planes in the literature, but none of the existing approaches bootstrap the system with regards to all the properties which are required by an industrial network, which include the automated switch management IP provisioning, automated controller list provisioning, resilience of control flows, multi-controller support. However, many of the approaches already assume proprietary switch extensions, which might not be ideal if we want to work with off-the-shelf devices. And the proposed approaches here fulfill all the objectives. Additionally, what maybe must be noted at this time is also that existing approaches do not provide any open source implementations of their designs, while we do. So the question might arise, why do we even regard RSTP or spanning tree implementation? Well, spanning tree is very beneficial for the effortless controller-to-controller connectivity due to the switches being able to automate the spanning tree computation and forward the controller-to-controller packets. However, our STP comes also with two caveats. And one of them is that we eventually have to disable it to provide for the full visibility of the resources in the network, to provide for a full graph readout in the controllers. And dimensioning the RSTP timer and to know when to disable it correctly is non-trivial. We have an analytical formulation of the worst case timer duration contained in the paper, but we do not include it in this presentation. The other part is that the added complexity in the data plane might lead to eventual failures and implementation issues of STP and distributed protocols in the OpenFlow-based data plane. We next discuss the design of the two schemes. So, when we initially deploy our two schemes, the hybrid switch approach and the hop-by-hop based approach, in the hybrid switch approach, we assume a deployment of switch or the boot up of the switch in the standalone mode. The standalone mode relies on a heavy use of the normal port. Normal port is the port used for MAC learning-based forwarding of the packets. In the hop-by-hop approach, however, we assume that the switch starts up in the secure mode. Secure mode is the mode of the Open vSwitch-based OpenFlow agent implementations, where after interconnecting with an actual controller and establishing a controller-to-switch connection, the flow rules contained in the switch forwarding tables are not removed or not flushed, as is the case in the standalone mode. Additionally, in the hybrid switch mode, we assume an in-band mode enablement. In-band mode allows us to interconnect to the controllers with a set of basic flow rules which are pre-installed in the system. The hop-by-hop approach, however, does not assume the in-band mode enablement, but it assumes a set of other OpenFlow rules which are generic and which are specific to that particular switch, but can be bootstrapped basically using a simple boot up script and do not require any custom modification. The flow rules contained in the in-band flow rule set are basically used to interconnect the local switch port to using, let's say, OpenFlow session to the next neighbor controller, as well as to allow for propagation of a locally generated TCP UDP packets used for SSH and DHCP communication, as well as for ARP request handling from the switch to the controllers. As we can see here, and this is specific now to the hop-by-hop approach, we have the two rules colored orange here that allow us for controller-to-controller connection establishment that rely on the normal forwarding procedure. So this means that the packets are forwarding on the MAC learning implementation, which means that in a non-spanning tree-based enabled network, this could eventually cause potential broadcast storms. So in the hop-by-hop approach, we fight these initial broadcast storms with a set of meters used to police the problematic traffic which can actually cause broadcast storms, and in this case it is only related to these flow rules, basically the controller-to-controller traffic, and it policies the ARP controller-initiated traffic, as well as TCP synchronization and synchronization acknowledgement messages. Otherwise, these rules, as well as the meters in the first phase of our bootstrapping approach, are eventually disabled and removed. The hybrid switch phases 0 and 1 rely on intercontrol synchronization using a spanning tree, where eventually after the switch initially sends out a DHCP broadcast request to get an IP address, the controller, which is the leader of the system, responds with the DHCP lease, and eventually establishes an SSH session to that particular switch. Then the controller in the hybrid switch approach also enables the switch with the list of the controller IPs required for the switch to interconnect with its controllers using OpenFlow. In the hop-by-hop approach, the procedure is similar, except that in the hop-by-hop approach, we only allow for the configuration of the first neighbor of the controller, so the adjacent switches connected directly to the controller, while all the other switches are initially unable to communicate to the controllers. They will only be able to do so in the phases 2 and later, after the adjacent switch to the controller is bootstrapped with an initial set of flow rules. The output of the phases 0 and 1 is that in the hybrid switch approach, we now have switches with configured IP addresses and configured controller IP lists, and we have a spanning tree converged, computed automatically by the switches, and the controllers are able to communicate to each other. In the hop-by-hop approach, the controller, who is the master of the system, has now responded to its adjacent switch with the DHCP address lease. In the second phase, we actually establish the resilience of control plane flows, and in the hybrid switch approach, this means establishing the OpenFlow sessions between the switches and the controllers in first come first serve manner, as we discussed previously, as well as installing the initial flow rules and disabling the in-band flow rules in order to be able to override the Open vSwitch implement flow rules with resilient flow rules, which are custom computed based on the given graph of the topology. In the step 2b, we disable the rapid spanning tree in the hybrid switch approach, so in order to provide for unblocking of the blocked ports by the spanning tree computation. Eventually, we install the resilient flow rules. In the hop-by-hop approach, we also distinguish between two subphases in the phase 2. And specifically, we first establish the OpenFlow sessions in the hop-by-hop manner, and we install tree flow rules, which basically is a tree that emulates the spanning tree procedure, which is in the hybrid switch approach computed by the switches themselves. In this case, it is the controllers who basically gradually extend the tree and introduce new tree flow rules in every newly discovered switch, so in order to enable the discovery of the next hop switches. In the step 2b, similarly as above, the resilient flow rules are installed whenever possible during the bootstrapping of individual switches. In the phase 2a, in the hybrid switch approach, in addition to establishing the OpenFlow session, we also disable the in-band mode, as shown previously. And the initial flow rules contained here are basically more or less the same rules as the in-band flow rules provided by Open vSwitch by default during the bootstrapping procedure, but they are now custom made and they have a custom priority which can be overridden by resilient flows in the final phase of 2b. In the hybrid switch phase in 2b, now we also disable the RSTP eventually after the expiration of a RSTP timer, which is dimensioned as per our paper, and eventually the resilient flow rules are installed due to the graph being fully discovered by the controllers. So this is the resulting state of the 2b. Basically all the switches are bootstrapped and all the switches are able to interconnect to all the controllers, and all the topology elements are visible to the controllers. In the hop-by-hop approach, in the phase 2a, we are now installing the initial tree rules. After the OF handshake has occurred, the tree rules enable the interconnection of next hop switches to the controllers. And eventually every other switch can also interconnect to the controllers and go through the same procedure of phases 0, 1, and 2a. The tree rules are basically looking like this. Every switch, which is behind the adjacent switch of the master controller, they enable the forwarding of their packets, for instance for DHCP, OF, SSH, and ARP entries over to the master controller as well to the other controllers without any occurrence of loops, and thus they limit the possibility of broadcast storms occurring. As I mentioned before, the trees are incrementally computed, as will be shown in the next slides. In the phase 2b, we now eventually install the resilient rules after more than a single path has been found to the destination switch. So the resulting state of the overall bootstrapping in the hop-by-hop approach in this case is that the switches are now associated to all controllers. They all have their IP addresses assigned. And in addition to the base graph, which is the base substrate topology, the controllers maintain also a virtual topology, which is basically the rolled out tree, which might not be the minimum spanning tree, however, which interacts all the controllers and all the switches with the controllers as well. So the outcome of the both schemes after phase 2 is that we have now established k+1 maximum disjoint paths for control of the switch pairs. In this case, on the left, we only show the colored paths from S4 to all the controllers. And on the right, we also see control-to-controller pairs, which basically are redundant pairs established between every controller instance. To allow for dynamic network extensions in the hybrid switch approach after phase 2, we also have an additional subphase where we install minimum spanning tree computed using the Prim's algorithm. In the hop-by-hop approach, we basically use the tree which was computed and extended during the initial bootstrapping procedure, during the steps 1 and 2, to allow for discovery of switches and subtopologies and network cells attached to the backbone at runtime. We are also able to handle the failures of individual forwarding elements, which are elements of the tree, of the virtual tree used for the topology discovery and network extensions. Specifically for every failed element, we have an alternative tree which is embedded after the failure of an initial element in the original tree. We next discuss the evaluation of the overall approaches. We discussed the evaluation with regards to 3 key performance indicators, which are the global bootstrapping convergence time taken to bootstrap the network from scratch. Additionally, we consider the network extension time, KPI, which is the time taken to bootstrap a single switch from scratch, as well as the flow table occupancy, which is a KPI corresponding to the overall overhead of the bootstrapping procedure on the number of flow rules installed in the switches, which is especially relevant in switches with small TCAMs, for instance. We evaluate these 3 KPIs with regards to different topology types, different topology sizes, controller placements, and numbers of controllers. As was discussed before, we focus here on the industrial network deployments, so you will see that the impact of the topology type has quite some relevance on the expected bootstrapping convergence time, with, in this case, the star 4 topology converging the fastest to the final state of the bootstrapping procedure. As can be seen directly from this figure, in case of the single controller deployment, the hop-by-hop approach is much faster by the hybrid switch approach. And in the case of star 4, this speed up is almost 6-fold. Similar trend is observed for multiple controller case, except for the fact that the gap between the hybrid switch and hop-by-hop approach in terms of the global convergence time is somewhat reduced. This may have to do with the complexity of the hop-by-hop approach, which requires additional multi-controller synchronization steps due to its higher complexity, due to the tree maintenance and the resilient flow computation at runtime during the discovery of the individual switches, which simply results in a larger synchronization overhead and thus a larger blocking time in updating any parts of the distributed data store of the Open Daylight Raft-based cluster. With regards to the network extension time, the trend is again quite similar. We notice here that proportional to the number of the deployed switches in the topology, the network extension time appropriately increases. This relates to the fact that on average for deploying a switch to an existing backplane, if the overall path span is larger to reach to that switch, we on average also configure a larger amount of switches on the path, which means that we take a longer time to actually configure all the nodes for supporting the newly discovered switches with the resilient control flows. Additionally, we notice the gap between the hybrid switch approach and the hop-by-hop approach, which relates to the fact that hybrid switch approach in general requires also to disable the HTTP timer. So in order to ensure that any interconnection of a unknown network or network partition or even a single switch to an existing backplane will not result in potential broadcast storms in the newly discovered topology if only a subset of those switches have their spanning tree actually disabled. Finally, we also observed that with regards to the flow table occupation, the hybrid switch approach is somewhat more efficient than the hop-by-hop approach. This relates to the fact that the hop-by-hop approach also requires tree installation during the runtime, during the operation of the system, which results in a somewhat larger overhead due to the inefficient tree installations, but also due to the larger complexity in the initial phase of the system. We notice the same trend both for one controller and three controller deployments in all topologies. And we observe here that the ring-based topologies, such as a ring consisting of 16 switches, actually results in the worst case flow table occupation, which has to do with the probability that the majority of the switches actually have to host resilient control flows for any other switch increases, and is somewhat also affected by the controller placement in the system. With the ratios of per switch flow table occupations on the right side, we can also distinguish the impact of multi-control deployment on the overall flow table occupancy. Specifically, we observed the worst case for ring 16 system, where the difference between the one controller and three control deployment is almost threefold. We now have a look at the pros and cons of both approaches. With the hybrid switch approach, which relies on the RSTP, we have a more straightforward implementation due to the reliance of the spanning tree to interconnect the controllers and control the switch connections in the initial phase of the system. However, we here depend on a legacy protocol, which might cause implementation issues and bugs, as has been observed on a production-ready switch. It also leads to worse performance due to a requirement to eventually disable the RSTP. With the hop-by-hop approach, we have a better performance. We don't have a requirement on the legacy protocol, but its implementation is more complex and it has a higher flow table occupancy. The implementation of the both approaches is open sourced and is available on GitHub. We also have attached a Docker-based network emulator, which instantiates Open vSwitch instances in Docker containers, as well as Docker containers hosting the multiple controllers in the same repository. The link is also attached in the comment section below. The implementations are currently compatible with the Bourne SR2 release. It is executable on simple commodity PCs, and as can be seen here on a relatively mainstream laptop device, we were able to bootstrap 8.8 grid topologies without any issues with a single controller instance running. This said, there is some potential for optimizations of the overall implementation, specifically with regards to the rule compression. We could also look into tree merging instead of swapping the trees for network extension trees after failure of the individual elements. And we would like in future also to support concurrent multi-controller bootstrapping, which might however be an issue with the Open Daylight that allows only for a single Raft membership definition at the bootstrapping time of the system and does not allow for dynamic membership changes. So this way we could potentially speed up the overall bootstrapping procedure and offload the bootstrapping steps not just to a single master of the Raft cluster, but also distributed among multiple controller instances. With this said, I will conclude the presentation. I'm also including a set of references by the authors which have inspired this work. I'm very happy to take any questions via email, which is included in the comment section, or in the dedicated Slack group of SOSR. Thank you for listening.